talking about emptying, how much work is done to empty a container. Now, just like in force, it helps to figure out, all right, what are the variables that matter? So let's talk about the variables that matter. So here's a regular old person trying to suck fluid out of a cube shape, okay? All right, now, one person next to him, he's doing the same thing, but he put a whole bunch of straws together, so he's trying to suck the fluid out of this container that's way down there. Does he do more work or less?
More.
More. Why?
Distance.
Yeah, distance. So distance seems to matter. Distance matters. Okay? This guy or woman, instead of sucking out water from the container, is sucking out mud. All right? Whatever. So, does that mean more work or less work?
More.
More work. So, what would you say the issue is here? The variable is density. Actually, viscosity within the straw would matter, but we're not going to do that. The density of the fluid, yeah? All right. So then the last container, instead of being the same phase, it seems like it's the same phase, but it goes forever. This not forever, but does this make for more work or less work? Same. Doesn't this have more fluid to pump out? So does it have more work to do? Yes. Okay. So the point is then this. Does the area of the face matter anymore, or now does volume?
Volume.
Yeah, so volume matters. All right, so that said, the variables at issue are then distance, density, not mud, and volume. Okay, distance, density, and volume. And then why is it calculus? Well, there's a lot of variation between the layers. If I talk how much work does it take to move this layer, it's different than the amount of work it takes to move that layer because they are different distances. So you're just like in before, you're going to talk about, all right, how much work does it require to move that layer and how much to move that layer, and then we need to sum all the work of all the layers into one big emptying factor, right? So there we go. The variables are distance, density, and volume, and the mathematical relationship to work. Work is, gosh, what is work? Do you remember? Force times distance, yeah? Okay, now the force, won't it come from, actually let's talk about the force required. Isn't it going to be the weight density, which is in newtons per cubic meter, that's the weight density, times the volume, which is in cubic meters, that gives you newtons. That's the force component. And then the distance, we'll just typically keep the distance in meters. Now then, Newton meters, what are the units for that? Joules. Newtons meters is joules. The units for joules, the units for work are joules. Right? Juniors, have you done this in seniors? You got a major edge, obviously. Juniors, have you done it? Oh, did you? Okay, cool. All right. So why this requires calculus? Because each layer is moved a different distance. We need to sum infinitely many infinitely thin layers, which makes it calculus. What calculus? Differential calculus or integral calculus? Integral calculus. We need to do an infinite summation. Integral calculus is amazing. Go back. Sorry, if you can't read my handwriting, you'd be one of a million. All right. Come on, Sam. Come on. We're all waiting for you. Just kidding. All right. So say we look at an example or two or three or five. A rectangular prism with a base 8 centimeters by 6 centimeters and a height of 10 centimeters is half filled with water. So this seems reasonable. 8 centimeters would be about this. Well, that's maybe a little long. By 6 centimeters and a height of 10 centimeters. Is half filled with water. Half filled with water. You with me? So there's some little waves in that. All right. Now, if we throw a pump in this, doesn't matter. I know later on you'll feel like it matters where the pump nozzle is, but it doesn't actually. The pump is going to pump the fluid up and out of the container. So we need to just pump it to the top edge of the container. And then we're going to turn on the spigot and it's going to go out. Yeah? Pretty good art, huh? All right, how much work is required to pump all the water out over the top of the edge of the container? Okie dokie. Okie dokie. So, here we go. We need to place origin. Where do you want to place your origin? Bottom corner, so it's first quadrant. Let's place it there, shall we? All right, now, the more you write the big ideas, the quicker they'll get in your brain. So we just said the variables at hand are weight, density, distance, and volume. Okay, and I remind you again, that's the volume of a slice. So the weight density, what is it? It's water, 9,800. Constant, so you can feel free to put it up. Okay, now distance. This, let's say I looked at this sliver. This was, how tall was it? I can't even read my writing now. That's so cute with my picture. I can't read it. Okay? So would you agree there's a sliver of water at 2 centimeters?
Yes.
How high do I have to pump it? How far do I move it to get it out? 8, okay? So when the y is 2, the distance is 8. What about the one at 1? When y is 1, how far do I have to move it to get it up and out? 9, all right? So in every case, it seems like the distance is
10 minus 1.
10 minus y. The top minus the bottom, or the upper minus the lower. The upper here, though, is not the surface of the water, because I'm not just trying to get this sliver to the surface of the water and then let it go. I'm trying to get it to the top of the container and let it go. So the upper here is not the surface of the fluid, it's the top of the container. Or where you're pumping it to. It says to the top edge of the container. All right? What about that's the distance, we got the rho. What about the volume? Now that's volume. Volume is the volume of each slice. Not the volume in the box, the volume of each slice. So this green slice here, this sheet of water, what are the dimensions of it? Yeah. 8 by 6 by dy high. Okay? What are the limits of integration? 0 to 5 or 0 to 10?
0 to 5.
0 to 5. You're pumping water. Where's the water?
0 to 5.
0 to 5. Yeah, I know it's tempting to say 0 to 10 because the container goes, it's where you're pumping the fluid. The fluid is from 0 to 5. This then, just like force, this is where the fluid is. Not where the container is. The air, I don't care about pumping the air up top. I don't need to go at 10. I need to go 0 to 5. Okay? You follow? Throw that in your calculator, which I assume you could do. You would get an answer. What are the units now in work? Joules. Okay. All right. Let's not sweat the calculator. These are easy to put in your calculator. Don't worry about it. Okay? Let's go to the second example. You've got a hemispherical, that's not a hemisphere, you see it's a half cylinder. okay? Kind of a grill kind of shape. A lot of people make grills like that. So a container below is filled to a height of 2 meters. If the weight density is 8,000, what's the work done to pump the fluid out of a small hole in the top? So you need to get it to that hole, yeah?
Yes.
So the big idea of the day, work is the sum of many force over distance, but let's go more specific. Weight density,
Volume.
distance, and volume, right? The row here is 8,000 is given, it'll always be given. The distance is, well, that kind of depends on where I put my origin here. Where do you want to put your origin? When we do circles, where's the best place to put an origin? Right in the middle of the circle is the best place, okay? In force problems and in these, you've got to communicate where you put your origin. If it doesn't say in the book, you've got to give me a picture with the axes located, all right? All right, then if I put the origin there, then what is the distance I need to, oh my goodness, maybe I need to draw this a little better here. Let's draw this a little better, shall we? So it says here the diameter is 8, yeah?
Yes.
So this probably goes from 4 to -4, and this goes to
-4.
about a half hour, I think. Just do the it's on the calendar. I think we'll be good. Okay? And if I have to write you, what's your next class? Who? Yes. What's she getting at? Okay. All right. So back here down to -4. -4 is the bottom of the container, but we also need to probably locate the water surface, or yeah, the water surface, the fluid surface. Where's the fluid surface? It's at -2. Because it said the height of the fluid was 2 meters. Do you agree?
Yes.
Okay, so cool. Now I'm feeling ready. When I say the distance, I need to take this sliver and pump it to the top of the container. So how far, what's the distance? Upper minus lower. What's upper? 0. And what's lower? Y. 0 minus y. Let's check that. Do you agree there's a sliver here at -3?
Yes.
If I do 0 minus -3, that's 3. Does that make sense then? That I would take 3 meters to pump it up? Yeah, so it's working. All right, so 0 minus y, upper minus lower. The volume. Again, should I see any pies here?
No.
No. When I say volume, I'm talking the volume of this sheet, not of the cylinder. And that's a rectangular prism. So what's the volume of that green sheet? 2x. Okay, it's 2xy. Why isn't it constant like the previous one? This one is the same all the way up, but this one is changing. Isn't the base of this rectangle and the base of they're getting bigger? Okay, why 2x, not x? Yeah, there's symmetry. Okay, so 2x wide. What else? 12 long. And these problems, that length matters. Does this matter on those force problems? It doesn't matter at all. Okay, but on the work problems, the volume matters, not just the area, the volume. So that 12 goes in. And the height of those slivers?
Dy.
Dy. Do you ever use x on these problems?
No.
It's always. Okay, so the limits of integration. 0 to -4 to 0? -4 to -2. Okay? That looks good, right? We're all good?
Yucky poo-poo.
Yucky poo-poo, well said, I think. So, what is the problem then?
X.
All right, so x can't stand. We're integrating with respect to y, so this needs to be dealt with. How do we sub in for it?
Equation.
Yeah, the equation. The x and the y, when the x is this, the y, when the x is this, the y is that, when the x is this, the y is that, they're related by being on the circle. So what's the equation of the circle? Okay, do I want to solve this for x or solve this for y? I'll look for x in terms of y. What is x in terms of y? Square root of 16 minus y squared, yeah? Is that the right half of the circle or the left half? It's the positive x side. It's the positive x side. The positive x side is this side. So what the heck? Are we not getting it? Yeah, the 2 does that side. If I did, say I didn't do 2 and I did right minus left, isn't this negative 16 minus y squared? Yeah?
Yes.
And if I did right minus left, isn't it 16 minus y squared minus negative 16 minus y squared? Isn't it still 2 times?
Yes.
So don't worry about the plus or minus. The double takes care of the negative side. You're good to go. So it's 2, 8,000, negative 4 to negative 2, negative y. There's a 2 in there. And root 16 minus y squared. Y, whatever our answers are, it better be, doggone well better be positive. If it's not, you did something wrong. And the answer is in joules. You with me? Okay. So let's make a second to fight off the biggest mistake, which is to get the 2. Okay? So when you do force against a face, it's rho dA and the limits. The limits are, let's see, they're typically y values, yeah? So I'll go, now let's just go low to high. And rather than call it y1, y2, I'm going to call it low to high. Are you with me?
Yeah.
Okay. Now, that low and high on force, is it where the, yes?
So on the last one, I plugged it into my calculator and it had a decimal. So are they always gonna have? Because none of the other ones had decimals. So are they
Yeah.
always gonna be nice numbers?
This one is probably relative to the fact that it's circle and this is so gross. So it could be up there. Yeah, no worries. I will also say this, because the magnitude of these numbers are pretty huge usually. Sometimes there is a little decimal being different based on your calculator method kind of thing. I'll talk about that later, but don't worry about the AP test. That wouldn't be an issue. Good question, thank you. So on the force, these limits of integration, are they about the container or the fluid? It's where the fluid is, okay? That row is fine. D, in this case, does it stand for depth of the slice or distance you're moving the slice? That's depth, and depth is found by fluid surface minus y. A stands for the area of a slice. It's usually something dy, and that something could be either a constant, an x, or a 2x. But it's always just the area of a line, not the volume. I don't care how far it goes back. You with me?
Yes.
All right. Now then, if I talk work to pump fluids out, then it's rho d, I guess I'll say distance. I start writing these out so I don't mess these up. Rho distance volume. The limits of integration, they're still for the fluid level, y1 to y2 or low y to high y. That's where the fluid is. D, that's the distance, and you're almost always in the problems we do, they're going to be the top of the container minus y. for upper minus lower, because you're tightening it to the top of the container, not just to the fluid surface. In what kind of cases would those be the same? Would the surface and the top of the container be the same thing? Anytime it's full, it would be the same, okay? The volume, that then is like the area, but also with the how far back it goes, with the length of the container. It still has that, how wide is it, x or constant, it's still got dy thick, but it's also how long is the container, right? Alrighty, let's go here. A trough with a triangular face. Top edge 3, side 4, distance between the bases 7, filled halfway up with gasoline. Find the force the gas exerts on the face, find the work required to pump. Now, do you agree that if I put my origin here, then the equation relating them is not first quadrant? That's kind of stinks. Not first quadrant. Ooh. If I really want it to be first quadrant, what could I do?
Shift it.
Yeah, just say, forget that nonsense, I'm drawing it like this. Is it going to be the same force?
Yes.
Yeah. So no worries. All right, then. So that way it's great. First quadrant's better. Writing the equation's easier. Everything's good. Yes?
Can we put it in the third quadrant so you can put axes at the top?
You could put it the third quadrant. The reason I wouldn't is that because when you go to find these slices, you're going to have technically a negative x and a dy high, and then you have to write the equation of this, which is a line that doesn't go through the origin. So I could anticipate a couple yuckies to that approach. That would not go. It would make it considerably harder. Good question. Thank you. I do have an exercise later that where I'm going to make you put the axis in different places so you can see, wow, this is really not good and this is better and stuff. Okay. So, so we're going to put it there, and that's a great question. Thank you for me. Now, for force, oh, actually, let's mark our marks. Top edge is 3, side is 4 is what I intend, and the distance between the bases, this is 7 here. The bases are the triangles, just so we're clear. And that's the distance there. So if I were to draw this way, looks like that, yeah? You with me?
Yes.
Okay, keyword is filled half the way up. So it's only up to 2 with gasoline. There. All right. Cool. Now then, A, force is, review, try A. All right, let's see how we're doing with force. What is your distance? Or, sorry, d depth. 2 minus y deep is each slice. What's the area before substitution? X dy, okay? So each slice is x, y, dy high, and we need to replace x, yeah? So if x is, what's your equation relating x to y? Y equals 4/3 x. It rises 4, runs 3, don't use the 7 yet. And so x equals 3/4 y. dy from 0 to 2. Is that how you set that up? Okay, what'd you get for an answer, anybody? 6,600 Newton? 6,600. So that integral is just 1? Okay. Newtons, are we good? Cool. All right, right on. Try work. If you haven't already done so. Ready? Okay. What's distance now? 4 minus y. You need to pump to the top of the container. What are the 3 dimensions of volume you use? So this distance is, this dimension is x, dy, and 7. 7 and dy are cool, but what goes in x's place? 3/4 y. And then limits of integration, now 0 to 4, or still 0 to 2? 0 to 2. And what are the units with joules? Or sorry, what are the numbers with, what's the answer with joules? Yes, ma'am. It's because we're talking about the work it takes to pump the fluid out of the container. So when I say what are the bounds, they need to be where the fluid is, not the container. Once I get up here, I'm not really, that's just air up there. So I only need to focus on where the fluid is. And that's for both pumps, okay? All right. Try this one. This one's good. Let's do it both, okay?
I used to just throw this on a test without ever having practiced it, and it didn't go very well. Students are all angry. But if you could think calculus, you should be pretty good.
Okay. You have a force answer or work answer or both? Should I give you another minute? Okay. I'm almost done. You better be done too. Okay. Let's all say our force answer together. Ready? Go. Okay. All right. I have 12,315. Do you concur? All right. What's the depth? 1 minus y. What's the area? Now that's the area of this line, which if you take it and unwrap it, it is just a line. How wide is the line, or the basic line? 2 pi r, and how high? dy. So if you're thinking pi r squared, I hear where you're coming from, but you don't want the area of the circle itself. You want the area of this line as it wraps around the outside. And so it's 2 pi r, what's r? 0.4 dy from 0 to 1, okay? Now for the work, let's all say our answer to that. Ready, go. 2,463.0. I got 0.1. Oh, okay. I'll be interested. All right, so would you agree that rho is still 9,800? What's the distance you need to pump the fluid to get it out of the top of the container? 1 minus y. When I say the volume, that's the volume of this little sheet of water. What's the volume of that? What's the area of the base? Pi r squared. And what's the height? dy. From 0 to 1. And so that is where we're getting something I said, 2,463. Oh, another point's rounding. Did you guys get more decimals than 100? 0.0. Okay, mine must be set to less than 3. Yikes. All right, what are the units there? Joules. Cool. This is on tonight's homework. I'll let you struggle with it. It'll be lots of fun. Okay, questions on last night's homework? Questions on what? Oh, sure, hit me, I'm sorry. Yes, yeah, absolutely. Okay, so when we talk about the area, we're just talking about, this whole problem is about how much force is being applied against the outside of the container. So I don't really care what's going on inside. Don't think when I say area that I'm referring to the area of the water slice. It's how much area is there to this line, because that's where you're feeling the force. On the outside of the container, that's what's feeling the force everywhere. Okay? So area is a reference to how much area in that line, and this line, and so on. Now, it's hard to find the area of a line unless you think of it as, oh, I'll take it like a string and just cut it and unwrap it. So when I say area, I'm really going to find the area of this red line. And when I unwrap it, then the width of it is just 2 pi r, the circumference. And the height of it is just right here, that's a small change in y dy. So that's where I'm coming from on 2 pi r dy. You follow? Okay. Now this, when I say the volume, I am now talking about I need to move this whole thing, not just the outside edge. I need to move this whole sheet of water out and up. And so then when I say area of the base, I'm really referring to that whole cylinder. And so that's why here I'm using pi r squared, not just some kind of line. I'm not just trying to move this line. I'm trying to move that whole sheet. And so it's pi r squared now, and the height is d. Does that make sense? Yeah. Okay. This is a fairly rare case, but I want you to be prepared for every event. So, yeah.
For A, I got decimals. Am I doing something wrong?
Did anybody else get? Oh, maybe mine ran it. Did anybody get decimals after this? Oh, sorry. What was it?
0.043.
043? Yes? Okay, thank you. Yes, Gary, I guess totally my fault. Sorry, my calculator must be jacked up. Or I'm jacked up, sorry. All right, questions on sets, something or other? 18, 10, 22. Yeah, we'll get to all three of those, but we'll give it a go. Okay.
There's only 122.
Oh, which 22? There's only 122, but it's up front.
Skylar's just crazy.
Crazy, Skyler. All right, 22, 18 rather. Okay, did I replace 18 or is it like the book? Okay, so 18, two totally different approaches. What's the approach there? Is that ultraviolet voodoo or is that USO? That's ultraviolet. The other part, where it's xe to the x squared, what's the approach there? That's USO. So you should split it into two integrals and do them in two totally different methods. Okay? 10. Did I replace 10?
Yes.
Oh, good, because I was going to say that's the problem we haven't done before. Let me get that from you. 10. Oh, excellent question. Thank you. So, if I say, hey, what's the derivative of sine when the angle is in degrees? You should say, not cosine. You should say, I don't know. Because the derivative of sine in degrees is not cosine. And it's hard. If you left that blank, I'll talk about that first thing tomorrow. Just leave that blank and I'll talk about it. Okay? 22. If you have a question on 22, come see me and I'll try and get you in the right direction. Or come in 7th hour. It's due today.
Wait, but time's tomorrow.
What? Yeah, we're talking about tomorrow, but you're tuning it in today and you can leave 10 o'clock. Right? Right? Okay. Okay.
Radiant. Well, why did I just say
This history? Yeah. Okay, there you go. The lesson's online. Okay. If you want to watch the video, okay? All right, thanks. You're welcome.
I don't know why they let us get so much.